minus 2 dB till 550 megahertz. So any signal, now this is a second harmonic, or this is not a second harmonic, rather this is a spurious harmonic. If you want to see the second harmonic of any signal, so we have to bring it to that particular frequency, say like at 200 megahertz if we are keeping, and we want to see the second harmonic of this signal at 200 megahertz. We will remove the attenuator, decrease the signal which is being saturated, and now you can see this is the second harmonic of this 200 megahertz signal, which is at 400 megahertz, and the level is around 30 dB down. We can see with the help of this marker. Now you can see if I bring it here, the displayed frequency is 210 because it is not being magnified. So what we do is we'll bring the fundamental here, that is 200, and try to magnify it, and just switch on it first, and the signal is still higher. That is why you are seeing a lot of spurious. So we need to attenuate the signal so that it is not saturating the spectrum. Now you can see this is around 200 megahertz of signal. Now the marker, as you can see, the marker is displaying it at 200 megahertz precisely. If you switch off the marker, you are seeing 201 because it is still not at center. So if you bring it again to center, now this is a perfect center. Now you are seeing the center frequency is 200.6 megahertz, and if you switch on the marker and bring the marker precisely to the center, you will see it is same 200.6 megahertz. So likewise you can see the second harmonic is should be at 400 megahertz. Now this is the second harmonic, as you can see, 200.6 into 2. And now if I switch on the marker, you can see it is precisely at same frequency, 400.2. So the idea of marker is, by decreasing the sweep width, you can precisely see the frequency of spurious harmonics or harmonics, first, second, third, any harmonics for that matter, or any signal which is being displayed on spectrum. Now as you have seen, if we were to put a video filter, suppose, now you can see this is the graph of spectrum analyzer, and this is nothing but AWGN noise. This is additive white Gaussian noise of a spectrum, and any signal below this noise floor will not be identified by the spectrum analyzer. The sensitivity of spectrum analyzer is around minus 90 dBm. So any signal below minus 90 dBm, say minus 89 or minus 85, minus 91 or minus 92, it will not be able to detect, because the power scale, it goes in negative below 0 dBm. So as you can see, if I switch on the video filter, the level displayed will not be correct because it becomes an uncalibrated input, but the noise has been reduced with the help of this video filter. So now you can see that the signal is displayed better, but it is in uncalibrated mode. Here the noise has not been cancelled, so the spectrum is in calibrated mode. Now if we were to see the signal once again at 200 megahertz, we'll bring this to 200 megahertz and decrease the sweep width. Always bring the signal to center frequency and then reduce the sweep width. In order to bring it precisely, use fine control pots. Now as you can see, the display accuracy is 0.1 megahertz or 100 kilohertz. If I change the frequency of signal source 200.7 to 200.8, you can see the signal has changed from 1 square to second square. So that means each square is 100 kilohertz, and the accuracy of scan width is even better than 100 kilohertz, because we are able to amplify or magnify rather this signal to an accuracy of 10 kilohertz. This is the phase noise of the signal being generated from a source. So we are able to see this variations, that is the stability of the frequency source. So now we can see that the scan width is better than 100 kilohertz, and the flatness is better than plus minus 30 dB. Resolution of display frequency display is 100 kilohertz, whereas the scan width is much better, that is around 10 kilohertz, and the display is of course 4 digit here, and we are using 40 dB and 20 dB attenuators to read higher amplitude signals or high power signals. Input is always 50 ohm, and IF bandwidth is 250 kilohertz, because if you put this thing in the center and each division is 100 kilohertz, as we had discussed, by changing the source by 100 kilohertz. So if you see the IF bandwidth, 3 dB bandwidth, the 3 dB bandwidth is equal to one division, that is only 100 kilohertz. So you can say, even from the marker, if we were to read, because marker has only accuracy of 100 kilohertz, so you can see the marker is right now displaying 200.5, whereas on this end the marker is reading 200.7. so if you see, the IF bandwidth of this filter or spectrum analyzer is around 200 kilohertz, and the horizontal scan that we are providing is 0.25 to 50 megahertz, rather more than 50 megahertz, because we can entirely see the scan width of 550 megahertz. If we divide, it is much more than, horizontal scan width is much more than 50 megahertz, it's around 70-80 megahertz. The dynamic range of the signal, if you see, is 10, 20, 30, 40, 50, 60, 70 dB rather, because if I increase this signal, you are saying it is taking entire 8 divisions. So the dynamic range is better than 60 dB for this spectrum analyzer, and the linear X and Y outputs are to be set at 500 millivolt per division. Now we want to see the sensitivity of this spectrum analyzer. As you can see, we are displaying a signal strength of minus 57 dBm here. If you read, this is set at minus 10 dBm, and 4 times for this 10 dB attenuator, so the signal input is minus 57 dBm here from this signal source. And if we put a 40 dB attenuator here, as we have seen, this is a 40 dB attenuator here, now at this 40 dB you can see that it is displaying around minus 97 dBm. So minus 97 dBm, and the signal is still higher. You can see by adding video filter, you can see the signal, and the signal level is around 7 dBm here, 7 dB rather, and the calibrated frequency level is around minus 97 dBm. So with this you can see that the 7 dB of this signal, whose amplitude is minus 97 dBm, is being read. So the sensitivity of this spectrum analyzer is around minus 90 dBm.